Yeah, so what I want to talk about today is a particular type of machine learning, right? So there's lots of different kinds of machine learning. And the particular type of machine learning that we focus on is machine learning that you do based on time, things that are like forecasts or things that change over time. And what we're really focused on is event processing. This is what we're working on. So just to kind of like make sure we're on the same page in terms of what we mean by events and why we should care about this, right? So we focus on event processing because we see it as this unifying abstraction that we can use to apply to most of the most important kinds of data that we deal with kind of in enterprise, right? Many things are inherently events, so system logs or IoT data. And many things that aren't obviously events have a really natural interpretation. So if you have a database, you can do change capture out of that and produce a set of events. When we talk about events, we're just talking about a value associated with a particular point in time. And so what's interesting about this kind of view of the world that has time involved is that it allows you to ask questions about how the world is changing over time. It lets you travel back in time to see what you might have known in the past and use that to make a prediction about what happened later on. And so there's a lot of really valuable things you can do with this as your starting point, right? You can build interesting machine learning models that are forecasting the future or responding to changes in the current behavior of the system. You can build dashboarding, historical analysis. There's a lot of interesting stuff that's really valuable you can do on this. And so there's been a lot of work in the past, decade or so to make it easier to do this type of analysis in real time. So Kafka was introduced. There's been a number of advances on top of that. That's kind of the background of where we are. So just to kind of ground this in an example, let's take a look at this kind of trivialized version of what you might want to do with events. So let's imagine that you run a game of some sort and you're collecting some events about what your users are doing. You know when they win their games, when they lose games, when they talk to each other, when they purchase things. And what I want to show is if we look at these events as a table in this way, it's really hard to understand much, right? It's hard to get to questions of motivation, how we want to improve a user's experience. How can we make Brad's experience of this product better looking at this table? It's hard to say. We don't know why Carla is the one that spends the most money. Just because we can't get our brain around data in this format. And so what I want to look at here is what happens if we change the abstractions that we're using to reason about this exact same data. Look what happens if we lay this out as a timeline, basically. We put this on a horizontal axis where we can see what's happening over time for each user. I think what you can see now is that we're starting to understand these stories, right? We can start to see what's happening to this user. We can look at this first user and see that, oh, every time they win a game, they're posting on social media, they're bragging, right? This is the motivation that we can now understand for this user. The second user, maybe this game was a little too hard for them. We probably lost this user, whereas we could have made it a little easier to play and gotten more engagement. This third user, we can see now that they're getting frustrated. This is the emotion they're feeling when they go and make a purchase. They've been losing and losing and losing, but they purchase an upgrade or something and they're able to win. And this is what's happening with this user now. And so the key insight that I want to really drill down on here is that the abstractions that we're using to reason about this problem are critical to our ability to discover and understand the solution. So the perspective that we have on this is that working with real-time data, with event-based data, is difficult today because we don't have the right abstractions, right? So we can write low-level Blink stateful functions and things like that that deal with time, but it's hard to reason in those low-level interfaces. You don't want to write assembly code. And there exist higher level declarative languages for talking about these things like streaming SQL, but these are based on the wrong sort of mental model. They're based on tables that don't have order and things. What we really need is this top right box. We need something that lets you have a high level language for reasoning that's built on stream native abstractions. And so that's what I want to talk about today. We are going to introduce this idea of the timeline. This is what I want to talk about here. A timeline is a new abstraction that we've kind of built the Kaskada system, the event processing system on top of, that we think addresses these problems. So there's sort of two important things about a timeline. We saw these when we kind of switched from the table to this temporal view. One is that timelines are ordered by time. This is the first kind of assumption that we make in the timeline abstraction. And the second is that it's grouped by what we call an entity. This is a user or a product or something like that. And the first thing that we can see here is that there's a really clear kind of visual interpretation of what this timeline is. We took those events that were in a table, we can lay them out on a graph. We've got a horizontal axis that's time. We can talk about values as a vertical value, or we can plot them out as just records or something long time. And so there's an easy way for us to kind of think about this visually and to kind of see the problem that we're solving as we reason about it. So we've talked about, events, but we don't just want to know that events exist. We want to do something with them. We want to do things like aggregate them. So when you have this horizontal axis of time, you can start to think about, well, at a given point in time, what was the sum of all of the purchases that have happened? And we can compute that value using all of the events that occurred prior to that and have a value. This value will change as we observe new events. And the result of this is that we produce this kind of step function. So we distinguish between these two different types of timelines in the Kaskada system. The one is discrete values that exist at instantaneous points in time, and the other being these continuous functions that change as the result of aggregations over multiple events. So this is kind of at a very high level what we mean when we say that timelines are ordered and when they have a time axis. And the second thing I mentioned is that they're grouped. What this means is that every value is associated with what we call an entity. So in these examples, we're looking at a user. So different users have different events. And when we aggregate those events, we produce timelines that are associated with those same entities. So we started with 2 individuals that were making purchases, and now we have 2 purchase sums associated with those individuals. This just kind of simplifies some of the reasoning and aligns really well with the data model and the processing model that we use underneath. So far we've been talking about timelines in this kind of abstract way. We're up in this abstract world of timelines, and we need to have some way of kind of bridging from this conceptual idea that we have back to the actual data that we're going to work with. And there's a pretty simple way that we talk about doing this. So as I said, most of the event sources that we want to pull from in the modern data processing world can be described as events. We have tables or streams. You might have data lake, cold storage. And so with this timeline abstraction, what we do is we just interpret all of those data sources as a discrete timeline. So we have a kind of simple mapping that's lossless from the raw event data that we want to work with into a timeline. And then we can work with timelines, right? It's timelines all the way down. We start with a timeline, we do some operations on it, produce a new timeline. Maybe we produce a continuous timeline. It depends on what you want to do. But we work with timelines for all of the operations, and we'll look at what operations are supported. And then finally, we need to do something, right? We want to take this timeline and represent it as a file or some API calls or put it into a stream. And so we have a number of different ways that we can output this timeline. And so this is the sort of processing model that we have. We start with raw events in various forms. We interpret them as a timeline. We work with the timelines to kind of produce the computation we care about. And then we have different ways of producing outputs from those timelines. So as I said, our kind of point of view on event processing is that abstractions are really important. They really matter. What you've seen in this section is a new abstraction, the timeline, that gives you a way of thinking about data processing in a really intuitive, I hope, and visual way. The idea of this timeline is that it captures what's special about event processing. It captures the things that distinguish event processing from other types of data processing. And so instead of having to contort your mental model to account for all of those special things, you can just reason about computation using these abstractions that do all of that work for you. And that lets you really focus on what you care about, what you want to get done. So, we have the starting point of timelines. We looked at some of the visual interpretation of that, but they're pretty useless if you can't do anything with them, right? You want to be able to actually describe a computation. So let's take a look at the different sorts of operations that emerge from timelines as a foundation. So we already looked at one of these, the simple sum aggregation. So we said that you can imagine the horizontal axis as a temporal context. And so at any point in time, I can say, collect all of the purchase events that have occurred up until that point in time, and then compute a sum of them, right? So what this does is this gives you the history, the story of how that computation changes over time. You can go back in time and travel to a particular instant and say, well, how was this value different in the past? And you can see that as a change over time, rather than just as a single answer that's limiting you to what you know in this particular point in time. But maybe, going back to the operation, maybe you're not interested in all of the purchases from the beginning of time. Maybe what you only care about is what purchases have happened since the beginning of the month, right? So it's really easy to do this with the query language that we built in Kaskada. Here we just change the window to say since monthly, and now we'll reset the aggregation every time we reach a month boundary. And if you look at this month function here, this is just another timeline. So monthly basically is a timeline that has a true value at the beginning of each month. And we just use it in this since function to say, when do we want to reset this aggregation? So we'll see more of this in just a minute, but the point here is that it's, it's a kind of kit of parts that's pretty easy to compose in different ways. And so here we've got an example of this, right? You don't have to use this monthly or this daily or other periodic time aggregations as the source of your windowing behavior. You can use any timeline you want. In this case, we're going to say, how many times has someone viewed a page since the last time they made a purchase? Each time the user makes a purchase, we're going to reset the aggregation. And then each time they view a page, we're going to increment it, right? So it's a pretty simple explanation. We're moving through time. So, to be honest, the last few slides that we looked at, they're pretty basic, right? These are simple aggregations. But this slide here, I think, is a pretty big deal, right? It's easy to overlook what's happening here because the syntax is really simple. But what you're seeing here, this is a different approach to aggregation than what you get when you're using something like SQL. We're not just taking a bunch of values, assigning a group to them, and then rolling up within that group. What we're doing is we're walking through time and we're building up a value as we go. We're adding to it and resetting it as we move through time and as events occur. And I at least find this to be, a much more natural way of thinking about operations like this. It's better aligned to how I kind of interact with the world on a day-to-day basis. And we'll see that it doesn't just stop here, but just to kind of compare, this is the same query expressed in SQL, right? So this is long, it's hard to understand, and it's really brittle. It's full of like little tricks to be able to get you to the same result, right? We have to take two different tables and bring them together into a single set. So we're unioning them, which means we have to change the structure. We're using this particular type of windowed aggregation to construct this cumulative value in the second arrow, right? And then we're reusing that because in order to reconstruct this window since an event, what we need to do is we need to associate each page view to a group, and the group is identified by the most recent purchase. And so we're doing this thing where we count how many purchases have happened and use that count as a group identifier and grouping based on that and then counting within that. And, it's very not clear what's happening to me, at least. And this is the cost of having this mismatch between the abstractions that we're using to reason about the world and the problem that we're trying to solve. And this cost just grows, it cascades as the problem you're trying to solve gets more and more complex. So let's do some of that. Let's make this a little bit more complex, right? So if we come back to the timelines, there's a lot more here than just being able to aggregate in a different way, right? We've been looking so far at how you can go from events and produce these continuous operations over them, but you can go in the opposite direction too. In this case, let's look at what happens if we don't want to know how this aggregation changes every time an event occurs. We just care about when I make a purchase, tell me what the value is. Those are the only points in time I care about. I don't care how it changes in between purchases, right? This is really easy to do when you're working with timelines. We have this filter operation called when, which basically allows you to observe the value of a continuous function at specific points in time. And so we've gone from a continuous expression back to a discrete one. When we were looking at SQL, I made the argument that using the kind of wrong abstractions, in a sense, causes this cascading complexity as your query gets more complex. And I want to point out how naturally timelines sort of build on each other, right? So I said that we use timelines all the way down, right? Start to end, we're talking about timelines. And what we're seeing here is that the result of the previous slide, the timeline produced by that aggregation of how many page views have occurred since each purchase at the time of a purchase, it's just a timeline. And so now we can aggregate it again. So we can compute an average of that page view count across different purchases. So, look at this code. This is fairly easy to read, I hope. We start with some page views, we do a count, we filter, we take an average. Each of these lines has a kind of one-to-one correspondence to a fairly, I think, intuitive visualization that we looked at. Each line fully parameterizes what it's doing. We have this system that's fairly easy to reason about what you're doing here. And I want to look at one last feature of the language before we move on. So if you've been watching closely, you may have noticed that all of the examples that we've looked at so far have been for the same entity. They've all been for users. And obviously that's not good enough. We need to be able to work across entities. And so Kaskada gives you two different ways of working across entities. And we can see both of them here. The first is that you can change the entity that you're using by using a new entity key. So in this case, what we're doing is we're starting with a bunch of reviews, and then we're associating them with the product that's being reviewed. The second tool we'll look at on the next slide is a lookup. But what we've done here, just to kind of produce a value for us to work with, is that we've computed the average review score for each product. So we could compute what's the average review, for each person that makes reviews. But here what we're looking at is how are individual products reviewed and how does that change over time? So let's look at the second operation that we provide for this, which is what we call a lookup. And what we're doing here is we're coming back to the individual purchases and we're using them to look up the value of the product that was purchased, looking up the average score for each product that was purchased. So we start with the purchase, we use the product that's associated with that purchase as the key to do this lookup operation. And the lookup is looking up this value that we computed in the last step, which is a per product value. So one thing to notice is that we're preserving the time axis throughout this whole process, right? This join operation reflects what the review average would have been at the time each user made these purchases, even though that value is changing over time. The association stays the same. So what you're seeing here is that this is a way of effectively contextualizing the results that you're producing. So we can work across entities and understand how each individual purchase relates to a larger set of values. It lets you kind of normalize a specific value with respect to a larger population. So there's a lot more that you can do with timelines that I haven't covered here. But I'm hoping that this kind of shows you a flavor of where this is going and the possibilities. The sort of TLDR here is that you get all the sort of transformations, aggregations, and filtering logic that you would have been able to use in SQL, but you also get this new set of tools that let you deal with time and order in new and interesting ways. So these kind of flow naturally from this foundation of the timeline abstraction, and they make it a lot easier to reason about, you know, behavior, causation, change across time. So just to kind of like step back at the very highest level, what our argument here is effectively that the way that you express a computation, it shouldn't stand in the way of the questions that you want to ask, the problems you want to solve. The right query language ought to make it easy to express the questions that you care about. And so hopefully I've convinced you that this kind of framework of timelines makes it a lot easier to reason about questions that you would want to pose of event-based data. And so kind of stepping back to, you know, what the Kaskada project in a sense is. Kaskada is an event processing engine that we built based on this idea of timelines. Today, you can go try it out. I'll give you a link to the repo in a later slide. It's built on top of Apache Arrow, so it's really high performance. It's vectorized computations throughout. And we built it in Rust, which means it's a statically compiled binary. You can just download it and run it, and you're good to go. There's no complex installation or maintenance. One of the things that I didn't talk much about is the ways that this timeline abstraction allows a number of really interesting optimizations. So I'll just touch on one real briefly here, which is because of the model that we're working with, where information can only travel forward in time, we can incrementalize every computation you can describe. There's no operation that you can describe in our system that can't be implemented incrementally. So you can compute all the way up to today's data, take a snapshot of the computation as it exists after you've processed all the data, and then tomorrow come back and just start from there and only have to process the data that arrived over the course of that day. This is a really, really interesting way of kind of allowing you to amortize the cost of an expensive operation by doing it continuously. And it gets us to the kind of the streaming model. The project is Apache 2 licensed. We'll probably be contributing to either Apache or the Linux Foundation pretty soon. And it's under active development. DataStax is putting resources into this, and we're looking to grow the community. We have a big list of things that we want to improve and then we want to extend. We want to do better performance. We want to reduce latency. We want to integrate with more different systems. We want to make the query language better and more flexible and more powerful. And so there's a lot of ways that, you know, you can participate in this process. There's a lot of opportunity here to get involved in this and kind of help us move this in a direction that's beneficial for as many people as possible. And we want your help. Like, we want to build a vibrant, inclusive community. And so, you know, these are some of the ways that you can participate. You know, come try it out. Check out the repo on GitHub. Give us a star if you think this is interesting. We've got a Slack channel, so we would love to hear from you. So, you know, it's up to you in a sense how you participate, but we would love to hear, you know, if this is interesting to you, what kind of problems this solves for you. I would love to take some time and run through an example if you're interested with this. You know, we got a trial program that we're running to kind of understand how users get started and if there are things that are difficult. So we're very interested in participation. Please come check us out. And I guess I'll stop sharing and take some questions if there are any.
You can keep the slides shared.
Oh, that's a good idea. Yeah.
Yeah. Well, great. Thanks. Thanks. It's a great presentation. So Let's have questions from the audience. Again, just a reminder, if you have questions, you can feel free to post into the chat. We will go through the Q&A right now. And if you prefer to speak to ask questions, feel free to raise your hand. I can unmute you. You can speak to ask questions or do an open discussion.
So I see it. Oh, go ahead.
Okay, go ahead. Sorry.
I was going to say, I see Bill left a comment about look forward to hearing ways you can extract timelines in GPT-4. And that's something we're really interested too. There's so much interesting work happening in the large language model world. And I think that one of the things that we think is really an opportunity for a system like Kaskada is to expand the horizon of what the large language model can have access to, right? I think there's been a lot of work in external memory using things like vector databases or graph search to be able to provide not just a human written input to the system, but also some data to the system. So the system can infer from, who I want to ask you a question about some users. So I'm going to tell you about who their friends are. I'm going to tell you about what they've been doing over the past month or year or whatever. And I think that Kaskada is potentially an interesting way of providing some of that context from a really large data set that you wouldn't want to try to just, train the model over your full database of terabytes of events, right? Maybe that's doable, I don't know. But it's probably easier, especially in the short term, to just build some features that capture the domain knowledge that you have about what you know is important about your users or whatever your entities are, and provide that directly to something like GPT-4 to allow it to kind of use the generalized intelligence that it's developed. Oh, here's another. Okay, is it safe or wait? Let me start at the top here. Okay. Miles asks, when you spoke about average product review, you said it changes over time. Do you mean the average review that is being posted relative to all reviews? Yeah, so I think, the simple way of thinking about this is, at any given point in time, if you have a database full of reviews, you can compute what is the average, right? So let's take a look at this like simple example. Where was that? I should change my titles so it's a little easier to see these. Right. So we have a bunch of reviews, and at any given point in time, I can take all the reviews and compute an average. But that average is changing as new reviews happen, right? So it might be that they start out really high and then they go down over time because, I don't know, people stop liking the product as well. And that's what we're capturing here, just that anytime you have a temporal component to some sort of computation that you're doing, it's really beneficial to be able to have the full history of how it's changed over time. That may not be what you're asking, but that's how I'm gonna, yeah. Perfect. Bill, one milestone might be able to express queries in English. I've actually been working on that. So I have a little side of my desk project where I'm taking all of our docs and a lot of the examples we use as part of our CI suite and building a fine-tuning training data set for GPT-4 to see if we can basically teach it our query language. Results have been mixed so far, but it's been an interesting exercise. And then, Pernika, is it safe to say Kaskada can do data processing that can be done using SQL, but with less code in an incremental way? That's what we're shooting for. So, SQL has been around for a long time, and there's a lot of kind of dark corners to its syntax, and there's a lot of extensions. So I don't want to necessarily say that everything you can do in SQL, you can definitely do with Kaskada. But I think that conceptually, we're starting from the goal of having those types of operations be possible to do in Kaskada and to have them be easy to express, right? We want to have easy ways of aggregating, easy ways of making windowing operations, easy ways of doing, join operations and things like that. Just doing it in this kind of temporal context so that we have the full history that allows us to add those kind of time-based operations. Something I didn't talk about was, for example, you might want to shift things relative to each other. So if you're building a predictive model, you might want to say, compute a bunch of features And then an hour after the features have been computed, I want to compute a target value. I want to have an hour separation between when I'm going to make predictions and when I'm going to observe the results. And so when you have timelines, you can basically just compute those two things as different values, shift them relative to each other, and then sample your training examples. So. ORM bindings. We don't have ORM bindings yet. We have a Python client library that has a bunch of really kind of quality of life features around using it in Jupyter. So the Jupyter experience is, pretty smooth, and we've got some really nice like visualizations of results and things like that. But we don't have ORM bindings primarily because it's not, we don't mutate data. It's a query language. And so at least that would be my first. Honestly, we haven't really thought much about ORM bindings. We haven't gotten to that level of maturity yet. There may be a use case for that, but yeah. Sure. And then finance trading work. So I should probably quit before too long. So finance is, I think, one of the really interesting use cases that we have been talking with a lot of people about, just because, time series are really important to financial modeling. And forecasting is really important to financial modeling. And those are two things that I think, have an interesting kind of perspective on. So yeah, it's definitely one of the use cases that we have been working on. I don't have any particular case studies to share on that at this point, but yeah, it's definitely an interesting use case. All right. The recent average also needs to be time windowed, so a sharp uptick or downtick can be detected in that time slice period. I think so, I agree. Another type of windowing that I didn't show here, which is possibly related to this, is kind of sliding windows. So you might want to say, I want to compute an average over the past 5 purchases or something, so that we don't see large variations. And that's just basically it's a different, we looked at, we had this window since purchase. There's a different operator that you can use that is sliding over purchases so you can say basically sliding over 5 purchases. So does this use as an alternative to Spark streaming? So yeah, I think that we're working in a very similar space as Spark streaming is. I think Spark streaming kind of gets you back to where we looked at the beginning, where you kind of have to choose. On the one hand, you can write fairly low-level Spark streaming code in Java or Scala, or you can use, the streaming SQL implementation that they have. And if streaming SQL works for you, that's a good solution. If it works, definitely. But what we've seen is that the challenge with streaming SQL is that it starts by asking you to pick a point in time, and then you can use SQL as of that point in time. And what we've discovered is that initial choice of the time before you get to use SQL is really limiting, because many of the questions you want to ask of event-based data, the answer, or they involve multiple points in time. We looked at, for example, right here, we computed some values and then we reaggregated them. We computed a bunch of discrete values and then we took the average over time. You can't really do that in streaming SQL because you chose a time. And so if you're at a particular point in time and you compute a count, for example, you don't have the historical context to compute the average over time. You answered that question, you're at a particular point in time. So there's some limitations there. Can we use Kaskada Python code just like PySQL? Or if you can share the library name. Yeah, so I think I can just show you .io. So if you go to our docs right here, there's a really great, I hope, getting started guide. So this will kind of run you through a lot of what we just talked about here. And then if you go to the Hello World Jupyter example, this will show you how to install our client library. So it's, this is all you need, pip install Kaskada, and you're ready to go, basically. And then you can start building sessions and working on things. So there is a client library. That's the install command for it. Please check out the docs if you're interested.
All right, I see we have quite a few questions. Maybe let's take the last one. We have
But yeah, we'll do one more. And then again, if you want to ask more questions, there's a little link right here to Slack. Just join our Slack. I'm happy to talk to whoever is interested for however long. So just come ask questions in there. Since you're looking at finance, perhaps you can look at incorporating TA-lib kind of functionality for all moving averages, MACDs, et cetera. It opens up a whole different world. Yes. So that's something we have not implemented, but it's something we're very interested in. So, things like moving averages, all of the sort of standard time series operations, we haven't implemented them, but the processing model that we use is really well suited to providing those types of operations. And that's something that would be on that list of things we want to implement, and we would like you to come help